Okay, so hello everyone. Yeah, we are going to be talking about Arrow and pyarrow today. I hope you're having a great EuroPython so far. So first, let's do an initial hands up. So who is using Arrow nowadays? Just to get a little bit of, okay, who knows what Arrow is? Okay, could you explain what Arrow is, right? Okay. So I'm not sure if I can, but I'll try. So yeah, this is a little bit what we are going to be saying today. First, we are going to brief introduction who we are, what is Apache Arrow, a little bit of the historical there, and then we're talking about different ways of exchanging Arrow data around. So first, the three of us, so we are all Arrow committers and PMC members. Rok works, well, is independent, works on the Arctos Alliance, and it's mainly focused on Arrow C++ and Parquet. I work for QuantStack as a scientific software engineer, and I mainly focus on pyarrow, Arrow C++, and then general maintenance, CI, etc. And Alenka is also independent, works on the Arctos Alliance, and works on pyarrow and general project maintenance. So, yeah. We have a lot to cover, so if we don't have time for questions, you can grab us then, and yeah, with a coffee. It's also easier to ask questions. So what is Apache Arrow? So first, let's think about the initial problem. So in the past, well, I suppose everyone that is using some data processing or data tooling, in general, we have some heterogeneous systems. So we have maybe some exploration with pandas, then with polars, we use some DuckDB, Spark, etc. And sometimes we do all that together in the same notebook or in different things. So the thing is, all those systems need a way of representing this data in memory. So for example, if I have my column with 2 gigs of strings, I have to be able to know which ones are nulls, where the strings start, where they end, so everything like that. So in the past, there was not a way of representing this data in memory. Or there were several ways, let's say. There was not a standard way. So each one of these systems had to come up with their clever ideas of how to represent nulls, for example, or how to do these things. So every time you had to, read from Parquet to pandas, you had to convert how this Parquet data is represented in memory to the internal data from the others. So the idea okay, let's go to the XKCD meme, and it's like, let's build a standard, right? But in this case, it kind of worked. So Arrow has become the de facto standard for in-memory data representation. So all these systems can share data without converting that. So meaning that if I pass a pointer on where this data is in memory, the other system will be able to understand how this data is, and we don't have to copy, convert, serialize, etc. Okay, so this is the Arrow definition on the website. I'm going to try to break it down. So first, as I was saying, Arrow is a specification or several specifications, and we have a bunch of language implementations. So those are language implementations for these specifications. So we have lots of languages that are able to understand this in-memory format. Then Arrow is a toolbox, meaning that it's not only the specifications and the in-memory format, but we provide a bunch of things like compute, Acero, or other things within Arrow, and network exchange, as we will see later. And then, in general, the project is meant for building data processing tools. So lots of us use it with pandas or with polars, but as a dependency, not really using Arrow directly, unless we want to build some data tools ourselves. So some basics, columnar versus row. So we have our tabular data or a table-like structure, and if we have some transactional data, we are creating, let's say, subscriptions here or orders or something like this. And every time a new one comes, we can just append the new data for the new user, like age, subscribed, spent, etc. And if we do it in a row format, we will just append one row after each other. So like a CSV file format or things like this. Arrow is a columnar format, meaning that instead of appending rows one after each other, what we do is we put all the data that is from the same column all together. That it's better because, for example, if we want to compute the average spent for these users, if we want to do it with the first format, where we have rows, we would have to be jumping in a bunch of places in our memory. But if we want to do it in columnar format, we have all the data locality together, so it's much easier and it's more performant. Okay, there are several other advantages of having a columnar format, like SIMD optimizations. SIMD meaning single instruction, multiple data. Lots of processors nowadays come with SIMD optimization, so we can, with a single operation, operate over a bunch of data. Also, it allows us to do better compression algorithms, because if the data is more similar, then we have better compression ratios. So that's... Yeah, so some concepts about around Arrow. So we have here this table-like structure. This would be a record batch in Arrow. A record batch is composed by a schema and a series of arrays. Those arrays are of the same length. So like a table, right? So the schema is composed with a bunch of fields which have their name and their data type, and then the different arrays. If we look at some code, because we are in a Python conference and we want to see code, so that's how I would create this record batch that we were seeing. I just create a schema with the fields that we were seeing, defining what is the data type, and then I can create the array and just create the record batch. If I take a look at the record batch, I can just see the table-like structure that I was seeing. Okay. So what is the Arrow format specification? So when we talk about the Arrow format specification and how we were representing the data, is really how these buffers are laid out in memory. So for example, for the first column, this is an int 8, as I was saying, so it's a fixed length format. So we know that each one of the values is going to occupy 1 byte. So I just need 2 buffers to represent this in memory. One buffer that is going to tell me whether the values are valid or not. So how do I represent nulls? So we have one of the problems that we were saying before, and how this data is in memory. So with 2 buffers, I can put this data. So any tool that understands Arrow format, if I pass these 2 buffers, will understand that this is an integer, that an int 8 data type, array, sorry, and what are the values there. So the validity bitmap buffer is just a series of bits that tells me whether the value is valid or not. We can see the ones, it's ordered on least significant bit order. So the first bit is the right one. So the first one will mean that the first value is valid, so 26 is valid. Second one, meaning 32 is valid. Third one is 0, meaning null. So we don't know what's there, but we don't care. And fourth one is valid, so it's 46. So we know we have for an array of int of length 4. Okay, so for strings, it's a little bit different because we don't know how much each one of these strings occupies. So we require also an offsets buffer. The offsets buffer is only going to tell us where the string starts and ends. So the first string starts at position 0, and it ends at position 6, not included, so it's Robert. The second one starts at position 6 included, ends in position 13 not included, so we have Alberto, and that's how we represent. We don't require a validity bitmap buffer because it's optional, and we don't have any null, so we don't have to have it. Yeah. So this is basically what the Arrow format specification. There are lots of others because I'm not presenting I don't know, nested data or others, but we can understand that basically what Arrow is doing is saying how we are going to represent this data in memory. So here we can see the same arrays that I was showing before, and we can see that the first one has 2 buffers, the validity bitmap buffer and the data buffer, as I was explaining. Validity bitmap buffer is occupying 1 byte because we just have a byte of booleans. And then the data, which is 4 bytes, because it's an int 8, so each one of these integers is occupying 1 byte. And for the string, similar as I was saying before, we don't require a validity bitmap buffer, and then we have the offsets and the data, etc. So what is Arrow? Just a bunch of buffers, and how do we represent these and the arrays, etc. So yeah. It seems easy, but it took me, I've been working 3 years for the project, so it took me some time to understand. So let's go to the Arrow data exchange. So apart from that, there are a bunch of Arrow specifications on how do you exchange data, these Arrow data, these buffers, from one process to another, in the same process, over the network, etc. So this is a little timeline that we've created with the different specifications when they were created. So yeah. And this is a little bit of an overview of the specifications. As I was saying, we have the Arrow columnar format, which is the in-memory format. So how the data is in memory, like in RAM or in disk or wherever, because you can memory map a file or things like this. And then the different specifications. For example, if we want to do communication in the same process, we will take a look in the C-data interface, C-stream interface, C-device data interface, which Alenka will explain later, or the PyCapsule protocol for pyarrow. If we want to do communication between processes, we will be using the IPC for inter-process communication. If we want to communicate Arrow data over the network, we can take a look at the Arrow Flight RPC framework protocol, or one of the implementations, which is the Arrow Flight SQL, which is just to integrate with databases and exchange Arrow data over there. We also have Arrow over HTTP, which is not a specification because it's only like an implementation of sending IPC over the network. And then, slightly different, we have ADBC, which is the Arrow database connectivity, which is for clients that, imagine you want to connect to a database and you don't care whether they are using Arrow or not, but on your application you want to use Arrow data. So you can use ADBC, so it will query the network or wherever is retrieving the data, and it will expose Arrow data directly. If the communication over the network is Arrow, of course, it would be more efficient because you won't have to do like copy, convert, or the different things. But yeah, if it's using raw format, it will transpose this into Arrow data, etc. So that's pretty much me.
Okay. If I go back a slide, it's a nice slide. So I'm just going to transition to the first two columns. And then Rok will explain a little bit more in detail, as far as we can in this 15 minutes, 20, the second two rows, okay? In the back, can you see the slides pretty well, or, okay? Okay, thanks. So first of all, let's check the IPC. So the IPC is designed, it's a protocol, it's a specification just like the Arrow format for how to represent data, Arrow data in memory. Is the same kind of specification, but for how to move Arrow data. So if you have to go through the wire or to another computer or to another part of memory, if that's something you need. So how to serialize Arrow data, how to put them in a format that will be optimal to move, and then when you're on the other side, how to deserialize that, okay? So the way to go on the way, so how to move that, that's called the stream of binary messages. So that's kind of the format that we specify of how to move the data. And then on the other hand, we also specify, the Arrow specifies how to rebuild that data. So you're in a separate memory on another computer. You have this stream of binary messages. So how can you read that into memory and operate it as it would be Arrow data? That's also specified as a protocol, as a specification, and also it's implemented in every language that's included in the Arrow project. So Python, R, C++, etc. The right side, there's a small schema picture of how that binary message looks like. It starts with a header that explains to the end user what's in the message, and then the message is just kind of schema and all the buffers sequentially stacked one after the other and shipped. Okay? So it comes in two flavors, actually, the IPC. The streaming format is what we talked about now, arbitrary length of record batches sent from one memory part to the other or the other machine. Really good for transferring data over network. That's the goal. But there's an extension of it called file format. It's an IPC file or arrow file or feather file. It used to be called a feather file. So it's actually the stream protocol extended, where at the end of this binary message, you have a footer that indexes the record batches that are in that message. So you can have random access of the file, okay? So let's do a bit of a diagram so we can understand that hopefully easier. Raúl is laughing, because we're not sure if that's going to be easier. We'll see. So the blue part is a memory A, for example, my computer. So I'm operating on record batches, using pandas, and I want to share this memory, this representation with Raúl. He's in another country, and I want to send it to his computer. I use this record batch stream writer to serialize the data. So this is what we use that actually writes the stream of binary messages. In pyarrow, the implementation and the method we use is IPC new stream. And that what it does when it's finished, it creates a complete binary stream in a separate part, in a separate memory, okay? That's written down in a memory, and then you need to deserialize it with, in pyarrow, for example, you use IPC method open stream, and you read it, and you operate on the data as it would be a batch 1, batch 2, in, it's equal as it was before in the blue memory part. There's no extra copies here. You don't, deserialize and make a copy again and work on that. It's just understanding what's in that serialized message, okay? Very similar is the IPC file format. It's the same, only that we use record batch file writer because it adds this footer at the end. We use in pyarrow, you could use IPC new file method. It writes to the disk, it creates this arrow file, and then you can read it. If you just open a file with, pyarrow OS file, just open it and read it, it will put that, for example, one record batch from the stream into memory to read it. But we have, the idea of this random access is that you can use memory map. So we have a separate method that's built just for this case. And using that method, you don't have to, the computer will not put anything in memory. It will reference directly to the file and just read it out there. So if, for example, you have a stream it has really large amount of data, okay? So you take random access, you just, take the second batch only, but it's also very big. It wouldn't fit in memory, for example, right? So you can just, or two of those wouldn't fit, right? So you can read directly, okay? So this is the IPC. Now we're going to move to the C data interface. I'm going to try to explain it shortly because the aim of understanding C data interface is to eventually understand PyCapsule protocol that's defined in Arrow. That is really good for Python libraries to implement, okay? It's a specification, it's an interface on a C level. So it defines a C ABI, which is a stable definition. There's a structs. In this structs, you have information of the address of the buffers and additional information so you know how to understand what's in that buffers. What's the type, what's the data like. If you know buffer protocol in Python, it was influenced by that buffer protocol. So it's kind of the same thing, but it can be between languages, it can be between implementations, so it's kind of broader, right? But it's the same idea. The idea is that you don't have to depend on source of Arrow library and compile it and kind of have that, but you can have access to the C memory already, and you don't have to depend on Arrow library itself. You can just access the memory if somebody's already operating if there's Arrow data in memory. So it's a zero copy, and it's in the same process. Compared to IPC, IPC is meant for interprocess, so between machines, while C data interface is meant if you are having things in the same memory and you don't want to copy it, you want to share that memory and just point, and everybody can just use the same memory and not do any copies. Example of the IPC we'll see later is the Arrow Flight. Arrow Flight uses IPC. Example of the CData interface is if you want to move from polars to pandas without, from arrow to arrow or, any conversion, it just understands if it implements the CData interface. Another info, just so you are aware, it's not the only interface available. The C-Stream interface is built on top of CData interface to enable streaming. And also newer versions of the interface allow non-CPU memory. So they kind of have the CData interface idea for any kind of device. You can have it on CPU, on GPU, on FPGAs. So the same idea, but for other devices. Just so you are aware that exists. Okay, so the gist of my part is the PyCapsule interface. It was championed by Joris, Pandas core developer and pyarrow core developer. And it enables, easier use of CData interface for Python libraries. So what it actually does is the CData structs that we mentioned that define where the memory, the pointer, the address, and all the other information, it wraps them into a capsule. Capsule is part of the Python C API. So it's not implementing PyCapsules. PyCapsules are used. It does define, standardizes the dunder methods that other libraries can use. And if everybody has that implemented, the data can just be shared. Okay? Kind of understandable? Yeah? Similar to buffer protocol. Like if one library has that implemented and the second one also, you can just, the data is just the same. It doesn't have to do any conversions. That's the idea. The idea why the CData interface wouldn't be good enough or why this is better, it's more robust, the PyCapsule protocol, because capsules take care of the memory management, right? So you don't have to, before it could happen that, memory leaked or some other things if you weren't really careful, if you used pyarrow private methods, but now this is really robust and you don't need pyarrow at all. You can just use PyCapsules. You get, if you use these dunder methods, if you define them, just capsules are shared between libraries. Something interesting, so you are ready for further talks, for further information, so it's not just too much of information, but having something interesting to look at. We're going to see this in practice, okay? So PyCapsules, you heard about them now, so you know they exist, but you don't have to really know in detail. But you have to know that this is under the hood supporting all the exchange that's available now between Python libraries. For example, here we create a pyarrow array. We have an address down there, so you are sure you can copy-paste it and try it out yourself. It's today's date, the values, and you can just, ARR is a pyarrow array. You can just feed it into polars, into the series constructor, and it will just know which part of the buffer, which part of memory this is, and see, it's the same address. So now pyarrow and polars are operating on the same address, on the same memory, without doing anything, right? It's cool, right? Yeah. And you can do more. You can go to pandas, from polars to pandas. You don't have to do any from or for or any kind of things to make your day worse. You can just feed it into PD series, and it understands. It has the same address, the same data. Isn't that awesome? I mean, you can go to any kind of library that implements this. I don't know why it's fun, but you wouldn't just do that. But you can use IBIS, Arrow 3, GDAL, Narwhal, Squag, DataFusion, DuckDB, GeoPandas, QDF. They all implement them now. The link is kind of it's a comment with a lot of libraries that we're trying to support also. So take a look to see where we are currently. So why is this cool? Think that you have really big data that's, wouldn't be able to copy because it takes too much memory. So you don't have to copy. You can just do whatever you want without just accessing the same buffers. Okay, thank you. To Rok and to Flight. Thanks.
Another nice point about sharing buffers like that is also you don't duplicate the memory usage, right? Like you just have it in memory in one instance, so you can save on RAM. Okay, so I'm going to talk a bit about, I'm going to go into the direction of distributed. So once you're not on a single node anymore and you want to move your precious Arrow data around, you have several options. So the first one is Flight RPC. How many of you are familiar with RPC in general? Oh, okay, quite some. Okay, so I can go through this quickly then. So RPCs, are, as you know, then are frameworks for distributed computing that allow one node to execute routines on another node, right? And most of RPCs have some sort of language to define interfaces. So say in REST, that would be the methods that you have, like get, put, etc. Yeah, as a schema, they look like this. And if you can see my mouse, please note that here, when a client, or rather a server is more interesting, usually returns data to the client, there's a serialized step. And when the client receives this data, there's a deserialized step. So one of the optimizations that Flight is after is, of course, to get rid of this serialization, deserialization. So remove the work that's needed for that, and also the copy of the data. So what is Flight exactly, or more exactly at least? So it's an RPC framework that's built on top of gRPC, so Google's RPC library. So it's not exactly gRPC, right? But it goes a level higher, and it comes with some good parts and some bad, unfortunately, as well. But let's focus on the good, because that's more interesting here. So basically, what it is on the wire, the Flight's data packages are really just IPC format serialized with gRPC's protobuf. So a flight data message looks like this, right? There's a descriptor of the flight, of the stub that's being used. Then there's the header that includes the IPC header and body. So these are not really serialized or anything. They're just like copied from your local buffer into this part of the message, and then data continues on. So it's the same contiguous structure that you have locally. You're also sending over the wire. So it's really easy, first of all, to send and also to receive. So when should you use Flight RPC? So ideally when your client and your server both understand and use Arrow layout data, so columnar. Otherwise, you're not getting as many benefits. And when you're moving large batches of data over the network, and you shouldn't use it, or it's less beneficial to when you're working with row-oriented or small volumes that are hard to batch. So how does then Flight look like in this kind of communication terms? So a client will get flight info from the server. So flights need to be implemented by the server. So you get these nice stubs that you implement. And when the flight information comes back, it's basically you get the information about which endpoints are available and how much data you can get from it. And then once you have that, you can then in parallel fashion, which is another nice optimization here, get data from the server or multiple servers if you have them. And this can be parallelized ad infinitum, of course. And yeah, you get the data back, and hopefully all is good. This is the get part. There's also a put and exchange, where you do both get and put. But unfortunately, we don't have time to cover that. So if you're less fancy or you don't have time to do RPC, you can try just sending our Arrow over HTTP. So here's an example of that. This would be an HTTP client that receives basically a buffer of, well, an RPC stream that was sent as a buffer or an HTTP request, right? So first of all, we open a URL, we get from it, and then we throw that into IPC reader. And the IPC reader has now read the schema that we can use for whatever is it we're going to need it for, and then we can get individual batches from this reader. And similarly, on the server side, well, here things are a little bit more complicated in terms of objects, but basically we're taking batches from some local source, record batches that is, and we're serializing them, or rather just concatenating them into a sink, into a buffer through this IPC writer. And once we created a single batch, we then yield it, and then the server would actually serve this buffer, right? And then once that's served, you go on to the next one. So this is kind of like what a very basic sending of IPC would look like. And this, you can find this example on this URL, like with kind of batteries included. It works. So if you want to play around, that's the way. So further, if you want to get production ready, then there's ADBC. And this is Arrow database connectivity. So wouldn't it be nice if we could get Arrow data directly from databases, right? Like that would be a nice optimization. So the thought was, let's use Flight as a transport layer, and then write some abstract methods that would provide a server and use that for writing database drivers. So ADBC is really two separate things. One, it's an abstract API for interacting with databases and Arrow data. And then it's a set of implementations of that API in different languages and as a driver for different databases. So how does this then look in practice? If you look at the diagram, we have Postgres here. It returns raw data because most modern databases, I believe, are still designed like that. And then typically we'll have JDBC or DBC or some other protocol that returns raw data. Well, it serializes it, sends it over the network to your workbench. And then you deserialize there, and you're in raw data, and now you do analytics on it, right? So you do basically columnar operations. So that's like a serialization, deserialization, and then another copy here to go to columnar. That's many extra operations. So if you do ADBC, what happens is on server side, the driver will already marshal your raw data into columns, or rather record batches of columns, and send those as IPC and avoid a bunch of copying, and that will come directly as columnar data or tabular data here to your client, where you'll do actual columnar analytics. And here, because you must be wondering whether this is done yet or not, there's a bunch of drivers out there in different levels of maturity. I think DuckDB is a fun to try, right? And I think Snowflake, Snowflake should be pretty well done at this point. Okay, I think we go now to summary with Raúl.
Yeah, I think we are done. So I think we've seen a little bit over this. Alenka explained communication in the same process between processes, and then we went over communication over the network and ADBC, which is slightly different in terms of more. ADBC would be the tool that end users are using in order to just retrieve Arrow data from the database. The other tools, as we were saying, are more for library usage on where you are creating data tools, etc. So I think we might have time for questions. So yeah, let's go. Thank you.
All right, let's see those questions. I don't see any microphones here. So.
Hi. So thank you for the talk. Nice overview. I have two questions. One is, how stable is the PyCapsule API? Because on the web page it says that it's experimental.
How stable it is? I would say it is stable. I mean,
I would say it's time we think of removing the experimental
Okay,
text.
excellent. Great, thank you.
It's working well with a lot of libraries, so I think we can start the discussion of
We're now on third release?
yeah,
Third release and support.
even more. Yeah,
No big
it's
bugs?
1 year. No.
Okay, very nice. And second question is, does Arrow have support for locking when you do in-process access to the Arrow memory?
It's only C++, right?
How is the data is immutable in memory as it is now, or rather it's hard to write into buffers? We removed that foot gun early on, or rather it's locked in a closet somewhere, so you can still do it, but then it's your problem.
Other questions? Yeah. I feel like a talk show host.
Thank you. So for your opinion, what's the difference between the C++ implementation of Arrow and Rust implementation of Arrow?
Rok should answer that. He has experience with Rust also.
Yeah, so they're pretty close feature-wise. There's overlap of the community as well. I think if you're choosing between the two, you want to think about what your use case will be. So for instance, if you want to use data fusion, Rust seems like a natural choice. Yeah, maybe do you have anything more specific there to say? Maybe I can give a better advice like that.
Yeah, the ADBC seems like the first one was in there was data fusion. So I was just curious if also the PyCapsule. I was wondering if that implementation is also in Rust or.
I believe no.
I don't think that Python bindings to Rust implementation implement that. I didn't check though. I mean,
Okay.
I didn't see anybody talk about it or hear.
Yeah.
And it's quite new in Python too. So, but it's a good thought or a good thing to open an issue or like think about it because it's really good for Python community. This kind of protocol. Yeah, thanks.
But it would be relatively easy to pass data anyway between the two. So I would say maybe just think about your stack. Are you building C++ or are you building Rust at the moment? Like what will be easier to integrate into your current project?
Gotcha. Thank you.
In the end, all of them implement the specifications that we've been talking about. So it's what are you using? Are you creating a product which is built on C++? Then just use CMake to build and use Arrow C++. Are you building something on Rust? But Arrow is the same format everywhere. So that's why we provide a bunch of different languages and implementations. But the in-memory format is the same. So it's going to depend on your use case or what you want to use.
Gotcha. Thank you.
Other questions? Anyone? All right, folks, let's give another round of applause. Oh, there's another question. Wait. The applause will come soon, but first another question.
Sorry, I didn't know much about pyarrow, so it's a really raw thought, so it could probably be stupid. But like, I look at the Arrow Flight RPC framework, and I could imagine like a cluster kind of setting where you could set up a cluster where actual compute happens in either Polar, Spark, whatever. Is there something or someone setting it up? I know Dask exists, but it's different. Like, you could write pandas kind of code and it could run in a distributed manner because all the machines implement that Aeroflight client or server kind of thing. Is there someone or something, some project that is doing that? I'm sorry if it's stupid, I didn't know much about pyarrow.
I think there are a lot of talks lately about composable data systems, you know, and building, you know, separating like storage, compute, and all the different things. And I think that's an idea, and it's in line of, and yes, it can be done. I'm not entirely sure if a specific project about having like a cluster of flight servers and then. But that's the idea that Rok was suggesting. So you can do get flight info, and then it can return a bunch of different endpoints, and you can stream data from those. And I don't know if you have iceberg behind, and then retrieve from your different tables. So yeah, it's part of.
Yeah, from what we are aware of, it's mostly used for database drivers, for this kind of stuff, and yeah.
Okay. Any last questions? All right. Thank you so much, Raúl and Alenka and Rok. This was great. The next sessions will be starting.